Technical debt, a metaphorical representation of the costs associated with implementing quick fixes or workarounds in software development, has both positive and negative effects on software development. This study delves into the concept of technical debt, examining its benefits and drawbacks through an analysis of developer discussions. The authors argue that a nuanced understanding of these dynamics is essential for effective management. The study employs a qualitative approach, analyzing 30 hours of developer discussions from 3 software development teams. The data is coded and categorized to identify themes related to technical debt, including its benefits, issues, and management strategies. The analysis reveals that technical debt can provide benefits such as increased velocity, reduced upfront costs, and improved customer satisfaction. However, it also introduces issues like increased maintenance costs, decreased code quality, and reduced team morale. The authors identify several factors that contribute to the accumulation of technical debt, including time pressure, lack of resources, and inadequate testing. The study also explores the concept of technical debt interest, which refers to the ongoing costs associated with maintaining and updating software systems. The authors propose a framework for managing technical debt, which involves identifying, prioritizing, and addressing technical debt items. The findings of this study have significant implications for software development teams and organizations. By acknowledging the dual nature of technical debt, developers can make informed decisions about when to incur technical debt and how to manage its consequences. The study's results also highlight the importance of continuous testing, refactoring, and code review in mitigating the negative effects of technical debt. A large-scale survey of gray literature was conducted to gather collective opinions of software practitioners on technical debt, or TD. The study employed natural language processing techniques, including topic modeling and sentiment analysis, to extract main topics and opinions from popular technology forums such as Stack Overflow, Medium, and D-Zone. The data was collected using the keyword TD as the search query. The research aimed to identify commonly discussed topics, issues, and benefits associated with TD. Topic modeling revealed that practitioners frequently discussed TD in relation to code quality, testing, and maintenance. Sentiment analysis showed that opinions on TD were predominantly negative, with practitioners expressing frustration with the accumulation of TD and its impact on software development. The study's findings highlight the importance of understanding practitioners' perspectives on TD, as they face the challenge of managing or accumulating TD. The results can inform strategies for TD management and identify key aspects of TD that practitioners are most concerned about. Notably, the study emphasizes the need for future research to focus on AI-driven TD detection and management, as well as an analysis of the effect of TD on current software development methodologies such as DevOps. The study's methodology involved collecting data from a large corpus of text, which was then pre-processed and analyzed using topic modeling and sentiment analysis techniques. The results were validated through a qualitative analysis of the data, ensuring the accuracy of the findings. The study's limitations include the reliance on self-reported data and the potential for biases in the data collection process. Future research efforts can build upon this study by exploring the application of AI-driven TD detection and management, as well as investigating the impact of TD on software development methodologies. Analyzing technical debt in software development, this research paper examines opinions and discussions from 3 major tech communities: Stack Overflow, D-Zone, and Medium. Employing a systematic literature review methodology, the authors identify and analyze topics related to technical debt. Data crawling strategies vary across platforms due to differing API availability and policies. For Stack Overflow, the Stack Exchange API retrieves questions and answers containing tracing toolnames. Medium articles are obtained using Beautiful Soup with specific tags, while D-Zone employs a hybrid approach combining manual search and Beautiful Soup. The data analysis process involves 5 steps: preprocessing, informativeness filtering, topic modeling, sentiment analysis, and summarization. Preprocessing divides text data into sentence-level instances, followed by lemmatization and stop-word removal. Informativeness filtering uses a trained text classifier to identify sentences containing useful technical debt information. Topic modeling and sentiment analysis provide insights into the collective opinions of practitioners on technical debt, its implications, and potential solutions. The research aims to understand current trends and challenges in managing technical debt within software development projects. By analyzing practitioner opinions, the study sheds light on the complexities of technical debt and its impact on software development. The findings can inform strategies for mitigating technical debt and improving software development outcomes. This research contributes to the growing body of knowledge on technical debt, providing a comprehensive understanding of the topic from a practitioner's perspective. The data analysis process in this study adopts a 6-step approach, as depicted in Figure 2. It commences with preprocessing, where raw texts are retrieved and filtered for their informativeness. Subsequently, topic modeling is applied to identify the primary topics within these informative sentences. The selection of a suitable topic model is crucial for accurate results, with Gibbs sampling Dirichlet multinomial mixture, GSDMM, recommended for short text topic modeling. Domain-specific topic models can also be employed. Topic filtering is then performed to map each sentence to its corresponding topic, allowing for further investigation into subtopics or aspects within each general topic. Opinion mining techniques are subsequently applied to determine the collective sentiment regarding each topic in each aspect, providing a detailed reflection on the percentage of positiveness and negativeness for each topic. The interpretation of topics from lists of keywords is facilitated using ChatGPT-driven techniques, specifically the GPT-4 model, which has higher reasoning capacity and conciseness compared to its predecessor, GPT 3.5. A series of structured requests are entered to extract short topics related to each line of keywords, and the replies are structured to provide explanations for each topic. The AI-extracted topics are then compared to the original keyword lists for validation. The study emphasizes the importance of verifiability and replicability, with the complete raw data published in the replication package to allow for replication. The results of the study are presented in Section 3, which addresses the proposed research questions. Key equations and algorithms include the use of GSDMM for topic modeling and the application of ChatGPT-driven techniques for topic interpretation. The mathematical concepts underlying these approaches are rooted in probabilistic modeling and natural language processing. The figures and tables in this section provide a visual representation of the data analysis process and the results obtained. Figure 2 illustrates the 6-step approach, while the tables provide a summary of the topics extracted and the corresponding sentiment analysis. The content of this page builds upon the previous sections, which introduced the research questions and methodology. The data analysis process is a critical component of the study, and the results presented in Section 3 provide insights into the topics and sentiment related to the research questions. Limitations and assumptions of the study include the reliance on a specific topic modeling approach and the use of a particular ChatGPT model. Future work may involve exploring alternative topic modeling methods and evaluating the performance of different ChatGPT models. The authors propose a 4-step approach to extract topics from a large volume of textual data related to technical debt, TD. The process begins with preprocessing, where textual data is crawled from social media platforms, including Stack Overflow, Medium, and Zone. The data is then filtered to retain only natural language sentences, eliminating unnecessary content such as source code, URLs, and publishing dates. The Natural Language Toolkit, NLTK, sentence tokenizer is used to obtain a list of sentences from each article, and non-English texts are filtered out using the LangDetect Python package. Source code and HTML markdowns are removed using the HTML2 text package, resulting in a total of 3,044 sentences in Stack Overflow questions, 965 in Stack Overflow answers, 49,903 in Medium articles, and 6,801 in Zone posts. The second step involves informativeness filtering, where a naive Bayes, NB, classifier or the expectation maximization for naive Bayes, EMNB, classifier is used to identify informative sentences. A manually labeled training dataset is created, consisting of 50% informative sentences and 50% non-informative ones. The selection criteria for informative sentences require that the sentence explicitly discuss TD. The performance of the two classifiers is compared using a 5-fold cross-validation, and the NB classifier is found to perform better, with an accuracy of 0.843. The NB classifier is then used to filter informative sentences, resulting in 36523 informative sentences. The third step involves topic modeling, where the collapsed Gibbs sampling Dirichlet multinomial mixture (GSDMM) model is used to extract topics from the large volume of textual data. The textual data points are randomly assigned to a predefined number of clusters, and iteratively reassigned based on a conditional distribution. The upper bound topic number parameter k is set to 30, and the number of words for each topic is set to 30. The final step involves topic filtering, where the GSDMM topic model is trained with the 36,523 informative sentences, resulting in 20 topics. However, it is found that 35,521 sentences, 97.3%, are associated with only 8 topics, and the remaining 12 topics contain no more than 2.3% of the data. The latter topics are omitted, and the number of sentences and extracted topics are reported in Table 1. The author's approach demonstrates the effectiveness of using a combination of natural language processing techniques and machine learning algorithms to extract topics from large volumes of textual data. The authors present the results of their topic modeling analysis, identifying 8 main topics related to technical debt, TD, discussed by practitioners on social media platforms. These topics, listed in Table 1, include the true cost of TD, balancing short-term gain with long-term pain, and managing TD, a team-centric approach, among others. The first topic is further divided into 7 subtopics, which highlight concerns regarding the unpredictable cost of TD, the trade-off between short-term gain and long-term pain, and the need to balance speed and sustainability in TD payment. The subtopics under the true cost of TD include the long-term consequences of shortcuts in software design, the benefits and drawbacks of quick solutions, and financial analogies in TD. Practitioners often use financial analogies to describe TD, and the high cost of TD can have significant financial implications. The second topic, managing TD, a team-centric approach, emphasizes the importance of team effort and management skills in preventing TD from hindering future development. Subtopics under this topic include solving TD through team collaboration and incorporating regular reduction of technical debt into the product lifecycle. The author's analysis provides insights into the concerns and strategies of practitioners regarding TD, highlighting the need for a balanced approach that considers both short-term and long-term implications. The use of topic modeling and subtopic analysis allows for a nuanced understanding of the complex issues surrounding TD. This quantitative approach enables the identification of key themes and concerns related to TD, as summarized in Table 1. The findings of this analysis build on previous research, which likely introduced the research question, methodology, and background on TD. The author's analysis and findings provide a deeper understanding of the concerns and strategies of practitioners regarding TD, setting the stage for further discussion and analysis in subsequent pages. While the study's reliance on social media data and topic modeling may introduce biases and limitations, the results provide a detailed analysis of the concerns and strategies of practitioners regarding TD, highlighting the need for a balanced approach that considers both short-term and long-term implications. Future work may involve exploring other data sources and methodologies to validate the findings. Technical debt, or TD, is a critical issue in software development that can significantly impact the efficiency and quality of the final product. This section of the research paper discusses various best practices for mitigating TD, including the adoption of suitable tools and strategies, understanding and managing TD as a team, and the role of different team members in perception and decision-making on TD. In terms of best practices, practitioners emphasize the importance of cross-team effort in finding and fixing loops, as well as the need for clear understanding and estimation of priorities. They also suggest that isolating messy code is an effective strategy for dealing with unavoidable debts, and that having a solid strategy for dealing with TD is crucial. The paper highlights the importance of team collaboration in managing TD, as it requires a collective effort to understand the state of the code and its impact on delivery. Different roles within the team, such as general managers, technical staff, architects, and company leadership have different perceptions of TD, which can affect decision-making. Engineers play a crucial role in managing TD, as they are the direct inducers of TD through subpar code. Other roles, like security and data engineers, can also be influenced by TD management. Agile teams can adopt proper practices to reduce and track technical debt, with advantages including clean code linked to agile development and continuous delivery. Paying down TD in agile sprints is also discussed, with practitioners considering it the right way to manage and reduce TD. Agile sprint planning is important for prioritizing, tracking, and addressing TD using project backlog. This includes allocating resources for TD in agile sprints, prioritizing TD in sprint planning, and addressing TD in sprint backlogs. In the realm of software development, managing technical debt is a critical aspect that practitioners emphasize. It's essential to prioritize and understand its business impact. Focusing on technical debt within agile teams can help eliminate it as part of daily work. Prioritizing technical debt-related tasks in sprint backlogs ensures that technical debt is paid down regularly. The business impact of technical debt is a key topic discussed by practitioners. Unchecked technical debt can negatively impact development efficiency, product quality, and customer satisfaction. It poses significant risks to companies, including financial costs, reputational risk, and regulatory action. Practitioners recommend tools such as StepSize to help capture and track technical debt, quantify its cost to the business, and prioritize the most important debt. Technical debt also affects team morale and productivity negatively, while implementing a process for managing technical debt positively influences engineering team morale and customer satisfaction. Assessing the risk of technical debt on the business level is critical, as it can pose significant risks to the organization as a whole. Tools and metrics adapted to measure technical debt properly are critical to its management. Code editors and tools like StepSize, SonarQube, and Clockwork can facilitate practitioners in terms of efficiency and code quality assurance. These tools provide various useful features, including linking issues, prioritizing workflow, and generating reports. Technical debt, TD, is a critical issue in software development, significantly impacting maintenance cost and overall quality. The paper discusses various aspects of TD, including its measurement, management, and implications for product development. Understanding metrics to measure and track TD is crucial. Common metrics used include the number of bugs, code quality scores, and impact on maintenance cost. Tools like SonarQube are commonly used to analyze TD levels and violations. In product development, TD is often seen as a necessary evil. Practitioners must balance quality and speed, particularly in fast-paced markets where delivering new features quickly is crucial. This can lead to trade-offs between product quality and fast delivery, with teams needing to understand the implications of these choices. Managing TD in product development teams requires attention from various stakeholders, including data and security engineers, managers, and senior architects. These individuals play a crucial role in guiding the team towards sustainable development practices. The paper also discusses the need to balance new features and TD in software development. This involves strategic decisions about resource allocation, with teams needing to carefully allocate time and effort to address both new feature development and TD reduction. In agile projects, managing feature development and TD can be particularly challenging, requiring effective management of situations where new features may overspill planned timelines. Technical debt management is a critical aspect of software development, particularly in the context of feature development, code quality, and testing. It is acknowledged that technical debt, TD, is inevitable and can have a significant impact on the long-term sustainability and functionality of software. To address this, project teams must prioritize TD management alongside ongoing development tasks. Integrating TD management into feature development is crucial, as every new feature adds debt or creates a placeholder for future debt. Maintaining a balance between feature development and TD reduction is essential for code quality. This involves fixing bugs, conducting thorough testing, and implementing robust development practices. The role of testing in TD management is also emphasized. Testing is essential for managing TD, particularly in development environments with continuous integration and deployment. Automated testing can quickly identify and address bugs, ensuring that the development process does not add to the TD. Testing can also facilitate the practice of reducing the long-term cost associated with TD. In microservice architectures, testing and refactoring are critical for managing TD, particularly when changes in code and architecture are frequent. Effective testing practices can support the refactoring process towards maintaining a clean, efficient, and scalable codebase. Code review is also essential for TD identification and management. Automated code review tools can help monitor code performance, identify security issues, and improve overall software quality. Proactively managing TD and maintaining high-quality standards can be achieved through testing and code reviewing. The impact of testing on TD in software architecture is significant. Lack of testing can lead to an increase in TD or specifically architecture debt. Good testing practices, including design and documentation reviews, are essential for identifying architectural flaws and high-complexity areas in the code. Sentiment analysis of the discussion using the Vader method reveals the benefits and issues of each main topic. The analysis considers the percentage of positive, neutral, and negative sentences without considering the sentiment strength. The results provide insights into the opinions and attitudes of practitioners towards TD management in software development. The discussion highlights the importance of prioritizing TD management, integrating TD management into feature development, and maintaining a balance between feature development and TD reduction. The role of testing and code review in TD management is also emphasized, particularly in microservice architectures. The sentiment analysis provides a quantitative assessment of the opinions and attitudes of practitioners towards TD management. The sentiment analysis of technical debt, TD, reveals a mixed perception among practitioners. In topics such as managing TD and understanding the business impact of TD, negative opinions dominate, indicating significant concerns about the long-term consequences and business risks associated with TD. However, in topics like the true cost of TD, measuring TD, and balancing new features and TD in software development, there are notable positive sentiments, suggesting that practitioners recognize the benefits of addressing TD as a quick solution and the importance of balancing speed and sustainability. Subtopics within each main topic further illustrate this dichotomy. For instance, under the true cost of TD, the long-term consequences of shortcuts in software design are viewed negatively, while choosing quick solutions and incurring TD is seen positively. Similarly, in managing TD, solving TD through team collaboration and understanding and managing TD as a team are viewed positively, whereas the role of engineers in managing TD is seen negatively. In conclusion, the sentiment analysis highlights the complex and nuanced perception of technical debt among practitioners, with both positive and negative sentiments expressed across different topics and subtopics. This underscores the need for a balanced approach to managing TD, one that considers both short-term benefits and long-term costs. Figure 5 presents the sentiment distribution for subtopics across 8 distinct topics, denoted as T1 to T8. Each subtopic is represented by a bar chart, illustrating the proportion of positive, neutral, and negative sentiments. The z-axis ranges from 0% to 100%, indicating the percentage of sentiments for each subtopic. Topic 1, T1, comprises 7 subtopics, with a majority of neutral sentiments, except for T1.3, which exhibits a higher proportion of positive sentiments. Topic 2, T2, consists of 7 subtopics, with a mix of positive, neutral, and negative sentiments. Topic 3, T3, has 5 subtopics, with a predominantly neutral sentiment distribution, except for T3.3, which shows a higher proportion of negative sentiments. Topic 4, T4, comprises 4 subtopics, with a mix of positive, neutral, and negative sentiments. Topic 5, T5, consists of 5 subtopics, with a predominantly neutral sentiment distribution, except for T5.3, which exhibits a higher proportion of positive sentiments. Topic 6, T6, has 4 subtopics, with a mix of positive, neutral, and negative sentiments. Topic 7, T7, comprises 5 subtopics, with a predominantly neutral sentiment distribution, except for T7.3, which shows a higher proportion of negative sentiments. Topic 8, T8, consists of 6 subtopics with a mix of positive, neutral, and negative sentiments. The sentiment distribution for each subtopic is calculated using a machine learning-based sentiment analysis algorithm, likely a supervised learning model trained on a labeled dataset. This figure provides a visual representation of the sentiment distribution across various subtopics, allowing for a more nuanced understanding of the topics and their associated sentiments. This information can be useful for applications such as opinion mining, sentiment analysis, and topic modeling. However, the figure has limitations, including the lack of information on the specific sentiment analysis algorithm used and potential biases or errors associated with the sentiment analysis process. Additionally, the figure does not provide insights into the context or the dataset used to generate the sentiment distribution. Technical debt, a pervasive issue in software development, has been examined through the collective opinions of practitioners gathered from various technical forums and social media platforms. The analysis reveals 8 key topics, including technical debt in agile sprints, managing technical debt, a team-centric approach, understanding the business impact of technical debt, measuring technical debt, tools and metrics, technical debt in product development, a necessary evil, balancing new features and technical debt in software development, code quality and technical debt, and overall opinions on technical debt. In agile sprints, practitioners generally support allocating resources for technical debt and adopting a daily focus on technical debt in agile teams. However, addressing technical debt in sprint backlogs is viewed unfavorably. Team collaboration, tools, and strategies for reducing technical debt are positively received in managing technical debt, although unclear role definitions hinder effective management. The business impact of technical debt is multifaceted, with risk assessment and team morale and productivity viewed negatively, while the cost of technical debt on business development is seen positively. Measuring technical debt with code editors and tools, as well as using metrics to measure and track technical debt, are positively viewed. Conversely, measuring technical debt with SonarQube is perceived negatively. In product development, practitioners acknowledge the trade-off between quality and speed, recognizing the necessity of technical debt in fast-paced markets. Balancing new features and technical debt in software development is generally viewed positively, except for handling technical debt in continuous software development. Code quality and technical debt are closely linked, with testing practices on technical debt viewed positively, while data metrics and testing in managing technical debt are received negatively. These findings highlight the complexities of technical debt in software development, emphasizing the need for effective management strategies, clear role definitions, and balanced approaches to quality and speed. Technical debt (TD) management is a critical aspect of software development, as it directly impacts the long-term health and quality of the code. This study employs the Guided Spectral Matrix Decomposition Method, GSDMM, to model topics and the Vader Sentiment Analysis Method to identify positive and negative subtopics in TD management. The results, presented in Table 2, reveal that practitioners face frustration with recurring issues, such as unclear roles and a lack of involvement of development teams in TD management. This can lead to misunderstandings and ineffective TD management strategies. The overemphasis on business risk at the expense of technical debt can demotivate development teams and compromise the long-term health of the code. Furthermore, inadequate tools to track and measure TD are a significant issue, with developers relying heavily on SonarQube to track TD metrics, but this is insufficient to prioritize debt repayment and maintain code quality. The pressure to handle TD under agile development can lead to an imbalance between quality and velocity, resulting in the accumulation of TD and deterioration of code quality. On the other hand, the benefits of active TD management are significant. Quick delivery and fixes to the code base, high-level collaboration, and common ground among team members are all associated with effective TD management. Managing TD in the product development team, rather than the commercial team or boards, allows for a more concrete view of the TD status. Regularly handling TD in Agile can keep development teams interested and motivated, leading to a more sustainable and productive software development lifecycle. The study's findings provide valuable insights into the challenges and opportunities associated with TD management and highlight the importance of effective TD management in software development. The study's validity is addressed through a discussion of construct validity, internal validity, and the strategies employed to mitigate potential threats. The authors reviewed the research questions and classification schema independently and collaboratively to ensure construct validity. The source selection approach is described in detail to enable replicability, and a broad search string was applied to mitigate the risk of incomplete results. The study's limitations and assumptions are acknowledged, and future work is suggested to further investigate the topic. The researchers address the threats to validity in their multivocal literature review, ensuring the reliability and generalizability of their findings. To mitigate researcher bias, all sources were evaluated independently by at least 2 authors. External validity is considered, acknowledging that some documents may not have been properly indexed or available. Conclusion validity is ensured through the review of terminology and data extraction by multiple authors, with disagreements resolved by consensus. The study is situated within the context of related work on technical debt, TD, a metaphor reflecting technical compromises that negatively affect source code maintenance. Previous studies have investigated the impact and evolution of TD, highlighting ambiguity in its definition. Ernst et al. Surveyed 1,831 participants, proposing a technical debt timeline to improve management and tooling strategies. Other studies have surveyed developers' opinions on TD, identifying reasons for its introduction, elimination, and management. The current study differentiates itself from previous work through its scope, methodology, and size of surveyed opinions. It employed a novel approach using large language models, LLMs, for data synthesis and analyzed 2,213 posts and online articles in the Gray literature. The study aimed to investigate, collect, and classify developers' opinions into major topics, providing a comprehensive view of research opportunities and practitioners' suggestions. The findings highlight 8 major topics related to TD, including its actual cost, management approaches, combination with agile practices, business impacts, measurement tools, and its place in product development and code quality matters. The study identifies unclear team roles and insufficient developer engagement as top challenges in TD management. Active management and paydown of TD are found to facilitate collaboration in sustainable development practices. Future research directions are proposed, focusing on AI-driven TD detection and management, as well as analyzing the effect of TD on current software development methodologies such as DevOps. The study contributes to the understanding of TD and its implications for software development, providing a foundation for future research and practice. This research paper presents a comprehensive list of algorithms, methodologies, and key findings in the field of machine learning and artificial intelligence. The authors have meticulously compiled this list to provide an overview of the current state-of-the-art techniques and their applications. The paper begins by outlining various supervised learning algorithms, including linear regression, logistic regression, decision trees, random forests, and support vector machines. Each algorithm is explained in detail, highlighting its strengths, weaknesses, and suitable use cases. Next, the authors delve into unsupervised learning techniques such as k-means clustering, hierarchical clustering, principal component analysis, and independent component analysis. These methods are crucial for discovering patterns or structure within datasets without prior knowledge of the expected outcome. Furthermore, the paper covers reinforcement learning algorithms like Q-learning, SARSA, and deep reinforcement learning. These algorithms enable agents to learn from their environment through trial and error, making them particularly useful for complex decision-making tasks. In addition to these algorithms, the authors discuss several neural network architectures, including feed-forward networks, convolutional neural networks, recurrent neural networks, and long short-term memory networks. These architectures have been instrumental in achieving state-of-the-art results in various machine learning competitions and real-world applications. The paper also explores various evaluation metrics used in machine learning, such as accuracy, precision, recall, F1 score, mean squared error, and cross-entropy loss. Understanding these metrics is essential for assessing the performance of different algorithms and models. Finally, the authors discuss some of the challenges and limitations of machine learning, including overfitting, underfitting, bias-variance trade-off, and the need for large amounts of high-quality training data. They also highlight potential future directions for research, such as developing more efficient algorithms, improving model interpretability, and addressing ethical concerns related to data privacy and fairness. Overall, this comprehensive list provides a valuable resource for researchers, practitioners, and students seeking to understand the diverse range of algorithms, methodologies, and challenges within the field of machine learning and artificial intelligence.